Okay, as Shannon already mentioned, Dr. Jean Hunter. She is Associate Professor of Biological and Environmental Engineering at Cornell University, and she's going to talk about HI-SEAS, the Hawaii Space Exploration Analog and Simulation Project. Sounds very cool. I'll hand over to Dr. Hunter. Thank you.
Thank you very much. Thank you for coming out for this talk. I'm Jean Hunter. I'm the principal investigator of the HI-SEAS Space Analog Project, which is now in the planning stages, ready to be built on the Big Island of Hawaii in the lava fields of Mauna Loa, in order to provide a place for long-term human factors research and space analog expeditions of 4 to 6 months duration. Okay. So what are analogs? As Shannon explained to you just a little while ago, a space analog is a place where the environment or the facility replicates the space environment in relevant ways. And there are all sorts of different analogs. There are geological analogs, such as MDRS. There are operational analogs. MDRS, again, is a planetary environment. The NEMO, Antarctica, FMARS. And ISS itself is an analog in some ways for long-duration microgravity space missions. There are also physiological analogs such as the FARU, the NASA Bed Rest Center at University of Texas Medical Branch in Galveston, where experimental subjects are placed in a 6-degree head-down resting position for 60 to 70 days. Well, there's some shorter duration studies as well, in order to evaluate the effect of analog microgravity on the cardiovascular system, circadian rhythms, muscle and bone loss, and so forth. So this is an analog for physiological countermeasure research. Okay. So the NASA Human Exploration and Operations Mission Directorate has identified a number of risks associated with long-term human space exploration, and many of these can be fruitfully investigated in the proper Earthbound analog environment. Now, no analog is entirely faithful to the space environment, partly because there's that pesky unit gravity that you always find here on Earth, partly because the unexpected things that you might find in space or on Mars can't be duplicated. You'll always find unexpected occurrences, but they might not be the same as you run into in space. Okay. We can use analogs to test a lot of different things: equipment, communications, human-machine interactions, habitability, behavioral science. And some people ask, well, why do we need analogs? Well, computer simulations and design requirement checklists show you what the equipment should do and what it does do in a laboratory environment. But it takes a live test to show exactly what it does, how it fails, how long it takes until it fails, and how humans can reasonably interact with it in a space-like environment. Can you make repairs? Can you scale back your expectations and use part of the equipment to do part of the science? Can you move it to a different environment where it might be more useful? So you need an analog in order to discover problems, because you don't discover them, all the relevant problems in the lab. Only by using something do you find out how it fails and how to fix it. Okay. We can also use analogs to design systems, equipment, procedures in the context of use. The design cycle in engineering it alternates among identifying a problem, proposing solutions, analyzing the situation, down selecting ways to fix or design around the situation, building a design, testing it, and then you're back to identifying the problems. the closer the test is to the actual reality, and the closer that the design cycle is to the elements of use and to the designers actually doing the work, the faster, cheaper, and better the design can evolve. Okay. We can use analogs to integrate people and systems in realistic scenarios. The definition of a complex operational environment is an environment where human beings are reliant upon technology, interacting closely with technology, making quick, real-time decisions that may have life or death consequences. So a good analog of that would be a flight simulator. Here we have a picture of an underwater personal submarine, and I believe that's my buddy Kim Binstead in there. NASA has a similar facility called the NEMO, which is it's an underwater habitat in which 6 people can live for periods of a few days to a week or two. Okay. In order to have realistic human-in-the-loop testing, you need to test under conditions where both the equipment and the humans are well outside their comfort zone, as they certainly will be in space. Realistic scenarios have psychological components, not just engineering components. They may have components such as fatigue, physical danger, isolation, frustration, and so on. And the unexpected is always present. Human-in-the-loop testing of the ISS urine reprocessor revealed that it wasn't up to the task. It had been tested with real human urine on the ground, but once it got up to ISS, the urine that it was processing was much higher in calcium than Earth urine, and so now they are now redesigning it in order to achieve the design goal of 85% water recovery, not with Earth urine donated by Earth people, but with what they call enhanced urine and enhanced urine ersatz, which have the extra calcium representing the calcium that's lost from astronaut bones. And it's kind of creepy to look at the slides of this equipment and look at all the scale and to say and to realize that this stuff was an astronaut's bone at one point. Okay. So we need this human-in-the-loop testing in realistic environments. The better we know the realistic environment, the better we can design our analog, and the better we can tailor existing analogs to meet the exigencies of space-worthy testing. Okay. Now I'm going to switch for a while to one of the Mars Society's flagship analog environments. This is the FMARS up in Houghton Island. This habitat is an excellent way, it's an excellent place to test human factors, questions of crew autonomy, crew-to-ground communications, crew roles and how they evolve over a long mission, and the psychological effects of isolation are becoming increasingly important as longer missions, such as a Mars mission, are being considered and developed by space agencies and also by our friends in the space exploration industry. Okay. FMARS research on long-term missions is relevant both to two-way and to one-way missions. NASA's analogs such as NEMO and DRATS, desert rats, are not well suited for long-term studies. They're more suited, NEMO is more suited for short-term human studies. DRATS is more suited for brief human-in-the-loop testing of habitat components and equipment performance. If we look at serendipitous analogs of long-term missions, such as Antarctic winter obers or submarines, these actually do not have the people in those environments don't have astronaut-like crews or duties, and generally the group of humans there is much larger than one might expect for an early stage mission. The Mars 500 was very, very expensive to run, and also the people in it underwent no real danger. if anybody had become seriously ill, they would have been pulled out before they were in any real danger. If the crew had come to really harsh words or blows, they would have been rescued before they did each other harm. Okay. As an analog of long-term spaceflight, the ISS is better because it's a microgravity analog, but it's amazingly expensive to run any sort of test in ISS, not only because you have to lift everything up there, and not only because there's a really long waiting list, but because everything that you take up there has to be tested and vetted to within an inch of its life for flight compatibility and safety in the space environment. And neither one of these really addresses, neither the Mars 500 or ISS is a practical place to address issues of human and equipment testing in a planetary surface context. Now, FMARS 2007, where my co-investigator Kim served, had 7 crew members, 6 in sim and 1 sort of support person who walked around with a rifle just in case a polar bear ambled a little too close. The 6 in sim crew members kept a strict simulation. They only went outside in a simulated EVA suit. They ate freeze-dried and dehydrated food. There was a communications delay. For a while, since they were above the Arctic Circle, they were even able to simulate the day length of a Martian sol versus an Earth day. And their mission was for 4 months, which was 4 times longer than any previous stays at the facility. During that time, they conducted geological, biological, and human factors research. Okay. You can see here the FMARS. Okay, that's a picture of it. It's actually very much like the Mars Desert Research Station. Here is where it is in northern Canada, and here is the Houghton Impact Crater on Devon Island, where the FMARS is located. Now it's extremely, it's a great place to be, but being so remote, it's quite expensive to conduct research up there. Everything that goes up there has to be airlifted in little twin-engine planes with skilled bush pilots. They can only fly when the weather is really good, and they don't carry much, so multiple expensive air missions are required to supply an FMARS mission and to get the people up there and back. Okay. But here are some shots from FMARS. Here again, where it is in the world. Here it is in the spring or fall snow. Here are some of the crew members on the Arctic permafrost near the station. Here's a view from inside FMARS in the laboratory, and I actually think this one is MDRS because it seems to be much more mountainous than FMARS, but it's Mars-like, isn't it? Okay. Here's the habitat layout of FMARS. If you take a mirror image of this, you get the MDRS layout. What we have here in this habitat is a 2-story tuna can configuration. On the first floor, there's a primary airlock, which is where you go in and out. There's also a secondary airlock so that a support crew member can go in and out to deliver supplies, to tend the generator, to check for polar bears and so forth, without interfering with the official in-simulation use of the primary airlock. Down here in the basement also is the laboratory and work table, a laboratory refrigerator, a prep room where all the EVA machines equipment is kept, a shower and a toilet. And then there's a ladder going up to the 2nd story. And up here in the 2nd story, okay, we have a communication work area where the computers are, a galley with a little refrigerator, sink, cooking area, a table where people can gather to eat, to meet, to talk, and to play games, and then 6 staterooms. These these beds here are actually lower upper bunks where each bunk is stacked on the other one, and the rooms are kind of strangely shaped because the lower bunk and the upper bunk are actually in separate rooms. It's a bit difficult to explain. Okay. Here's a picture of the food at FMARS for the 2007 season, and you can see that there's a lot of stuff in cans and bottles. There's seasonings. There's stuff that's easy to fix, like like pasta with tomato sauce, ramen noodles, of course, rice, beans, tortilla chips, snacks, freeze-dried and prepackaged meats and vegetables that allowed the crew to cook for themselves and even to do some really interesting things like making cheese out of dried milk. Okay. And that's Kim up there, who's a cheeseaholic, and you can see how blissful she is there to be able to have some cheese for dinner. Okay. And one of the things that they initiated over there was the practice of being able to cook something special for people who are having a hard time or were homesick. So this dish is a poutine. It's a French-Canadian specialty of French fries with gravy and different sorts of sauces and fresh cheese curds. I think it's probably an acquired taste, but if you ask any French-Canadian, they'll defend it to the death, and that's exactly what happened that day. Okay. Now, there are problems with a lot of analog environments that, to fit them properly to the kind of study that's being done. When you read about analog environments, often the crew is not astronaut-like. The environment is faithful to the wrong constraints. Here in the biosphere, for example, they looked at being faithful to different ecosystems on Earth. The crew number is small, and studies are almost never repeated. Okay. So we're building a habitat that will address some of these risks that are relevant to NASA. We'll put 6 crew members in there for 4 months to mimic the surface exploration phase of a Mars mission. They'll be doing real field work in the lava fields. They'll have Mars delays on their communication, limited access to water and electrical power. The crew will be astronaut-like, and best of all, we'll be able to do it again the next year. The central study in high seas is going to be a food study where we compare prepackaged food, like the one you see on the left, with crew-cooked food, as you see on the right. That's a MDRS slide. And there are going to be secondary studies on usage of water for crew hygiene and dishwashing, and of electricity for cooking. Because if we're going to plan a galley on Mars, we have to know how much water and how much electricity to plan for. And then we're also opening up the habitat to opportunistic research. That is, proposals from external researchers who are interested in testing something with an astronaut-like crew over the period of 4 to 6 months. And that's where all of you come in, because some of you will have great ideas that you'd like to test and that we would like to help you test. So are you interested in telemedicine or in new medical sensors? Are you interested in how the space in a habitat is used, crew dynamics and roles, design of spacesuits, robots, whatever you're interested in? We're interested in talking with you either for the first season or for subsequent field seasons. Here's a shot of the High Seas candidate site with Kim here on a dirt road among the lava fields. You can see how barren it is. We're very near to some interesting lava tubes, some cone craters, cinder cone craters, and other different kinds of lava and other interesting geological features that we hope to map during the first few cruise. We've already selected our crew for the first season out of a group of nearly 700 applicants. We winnowed them down to about 30 based on their paper records and recommendations. We interviewed them, and then we took the last 9, whom you see listed here, over to Cornell for team and leadership training so that they could all get to know each other, and also training with a chef, that's Rupert Spiess on the right, in using dehydrated and shelf-stable foods to make really good meals in a small kitchen. After the first mission, which we intend to launch in March of next year, we'll be running a yearly cycle subject to funding, where there will be a 4 to 6 month analog mission, a refit phase where we upgrade it, where we enhance it to be a more faithful analog, and then 4 to 6 months of outreach season. The high seas is actually portable. It's not a permanent facility, so that it can be packed into a shipping container and taken to other islands or other compatible environments. And it's also expandable. We might be able to add a dome to it. We might be able to add shipping containers to it. I'm sorry I can't show you a picture of it, but we are in contract negotiations with a small company that's building it for us, and we're under a non-disclosure agreement. But come back next year and we'll show you all sorts of really great pictures of it. And our education and public outreach is going to be a large portion of the activities there, both during the during the missions, sort of the way Dawn Pettit does it on ISS, and during the off season. So if you're intrigued by this, we invite you to contact us at the emails there, to volunteer to help us with mission support, to advocate for an ongoing high seas program with year after year of good science and effective outreach, and to propose research and outreach projects that you'd like to do in collaboration with us. Thank you so very much for your attention, and I will bow to our MC here, his opinion as to whether we have time for questions.
Yeah, we have time for a couple of questions. Down here on the front.
Who's funding this project?
This is actually under a NASA project. We're planning parallel studies at the high seas, and a bed rest study. The bed rest study is actually already underway. Its focus is the hypothesis that microgravity causes nasal congestion, which leads the astronauts to have a different, to taste and smell their food differently. We're also looking at diets in the high seas project, but more from the viewpoint of resource utilization, and our crew members there will be controls for the bed rested crew, not in an exact sense, but in a general sense. Yeah.
Will there be an opportunity to explore lava tubes and to use those as a possible camp out situation?
Currently, we don't expect to send people into lava tubes, at least not very far. One of our crew members is a robotics expert, and we will be working with him and the robots that he's gathering to test, so that we can put those robots into lava tubes to explore. We can also test the durability of robots under the very challenging conditions of lava. Yes. In the back. Sir, in the back.
Is there a food inventory list anywhere, or a recipe list? This all sounds interesting.
Is there a food inventory list or a recipe list? The food study at High Seas is based on the food study that Kim and I have been doing over the last 4 years at MDRS, and we would never have succeeded in getting funding if we hadn't had these 4 years of experience in Utah, and we're very, very grateful to the Mars Society for furnishing us the opportunity to work with MDRS crews. There is, in fact, a food list. It's not published yet, and we are compiling recipes from MDRS, from our chef, and we'll have a website open pretty soon where you can come in and give us your favorite recipes using shelf-stable and dehydrated foods. So we expect to get some input from, say, the prepper communities, from backpackers, from the Latter-day Saints, because that community is really into long-term food storage. So In a month or two, you'll start to see those recipes appear, and at the end of the first cycle, we'll put up all the recipes for both NASA and the public to use and enjoy. Last question, please. Who are our target candidates as crew members in the HAB? We're looking for people that are astronaut-like. So at least 3 years post-baccalaureate with a science background and with some complex operational experience, technical climbing, piloting, small boat sailing, operating room, ambulance, this sort of thing. Also, people who are congenial and easy to get along with. Very important if you're going to be spending 4 months with somebody. People who are well-spoken so that they can participate in outreach, and people who can do more than one thing. Okay? And whose research, every one of our crew has a personal research project, even our alternates. For example, Crystal Haney, who's an ex-Navy pilot, she has a personal training business, and her project, even though she won't be in the HAB, she'll be helping the crew members maintain their physical fitness, and we'll be tracking their progress using various kinds of sensors. So that you have to have a project that is compatible with the HAB. We would be delighted to have you keep us in mind for future mission seasons. Okay. Well, I think I'd better close here, but I thank you all for your attention, and I look forward to talking to many of you later today.